Hello everyone. So in the last video, we saw how to do integration by substitution for indefinite integrals. And in this video, we're going to talk how to do it for definite integrals. And everything is pretty much the same except for a couple of modifications because definite integrals have limits in them. So let's see how it plays out. So basically the formula is exactly the same as before. So we're integrating f of g of x times g prime of x, right? We have a composition function times the derivative of the inside. Or sometimes if there's constant multiples, or it also works in some other cases, but this is kind of the prototypical case. So we have composite function times the derivative of the inside. If we want to integrate this, we introduce substitution u equals g of x. We use u equals g of x and du dx equals g prime of x to write everything in terms of u and du, and then we do the integration. So what do we now do about the limits? So we start with the definite integral. So these are the limits for x. So we integrated from x equals a to x equals b. And when we transform it to a definite integral with respect to u, we are going to have limits with respect to u. So they're going to be different limits, and we get those limits by plugging in the old values of x into our equation for u and finding the corresponding values of u. So for instance, our lower limit is supposed to be when x equals a. And if we plug that into our equation, when x equals a, we see that u equals g of a. So the corresponding lower limit for u is going to be g of a. And then the upper limit in terms of x is x equals b. And when x equals b, we get u equals g of b. So all we have to do is find the corresponding values of u at the old limits for x. Okay. So as we said, it's pretty much the same as before. We just have to find the new limits. And one thing that's worth highlighting here is that once we have a definite integral with respect to u, all we have to do is find an antiderivative with respect to u and then sub in the u limits. So we never have to go back to the original variable x in this case. Unlike with indefinite integrals and integration by substitution, then we have to find an answer in terms of u and go back to an answer in terms of x. There is an alternate method where you could, do it instead of doing the definite integral, you could do the indefinite integral. That tells you an antiderivative, and then you would plug in a and plug in b and subtract them. So for instance, here in that case, you would integrate with respect to u, then you would go back to x, get an answer in terms of x, and then plug in the old x limits. That's also okay. I think that's a little tougher. So I recommend this approach where we just get an answer in terms of u and then plug in the u limits. But it's up to you. It depends on what you're more comfortable with. Okay, so let's see how it plays out in an example. So let's find the integral from 0 to 4 of the square root of 2x plus 1. We see it's a composition function. The inside is 2x plus 1, and it's a linear function, so everything is going to work out pretty nicely. So let's see how it goes. So we introduce our substitution, u equals 2x plus 1. Du dx is 2, so we can rearrange and write dx is a half du. And then since we have old x limits, x equals 0 and x equals 4, we should find what the u limits are going to be. So to find the u limits, we plug into our equation u equals 2x plus 1. When x equals 0, we have u equals 2 times 0 plus 1, we get u equals 1. And when x equals 4, we plug into our equation, we get u equals 2 times 4 plus 1, we get 9. So our new limits are going to be u equals 1 and u equals 9. And then we make a substitution and we replace the old limits by the new limits. Okay, so we start with the integral we had in the first place. We replace the inside by u, so we get square root of u, which I rewrote as u to the 1/2. Dx becomes a half du, so we're going to get du and then a half. And then we have to change the limit, so when we had 0 before, now we have u equals 1, and when we had 4 before, now we have u equals 9. And now, so there are three things to transform, right? The thing we're integrating, the dx has to become a du, so we have to have everything in terms of u and du, and then we also have to transform the limits, so we have to make sure we get all of them, don't forget any of them. And now we can forget entirely where this problem came from and just do it as its own problem. So we integrate with respect to u, we find an antiderivative. So using the power rule, that's going to be u to the 3/2 divided by 3/2, which is the same as multiplying by 2/3. And then we have to evaluate between 1 and 9, so we have to plug in 9, plug in 1, and subtract them, which is exactly what we did here. Right, so we see this is a relatively easy extra thing we can do, right, to find definite integrals. The only extra step is we have to transform the limits, and then we can plug in the limits without going back to the original variable. Okay, so there are two consequences of substitution that are worth pointing out. So let's suppose we have a function which is continuous on an interval from minus a to a. So this is an interval which is symmetric about the origin, right? That it goes a in one direction and a in the other direction. For instance, minus 1, 1, or minus 2, 2, or minus 50, plus 50, whatever, it's just an interval that's symmetric around the origin. Then what do we know? Okay, if we have an even function, which means that it's the same, on both sides, f of minus x is equal to f of x. Then if we integrate from minus a to a, f of x, that's twice the integral from 0 to a. So we're saying, if the function is the same on the left of our interval as on the right of our interval, right, that's what it means to be even roughly, Then instead of integrating across the whole thing, we could just integral from 0 to a, just integrate the right-hand side and multiply by 2. That would be the same. And then conversely, if it's odd, which means that f of minus x is minus f of x, which roughly means that on one side of the interval, the function is the negative of the other, then both sides are going to cancel. So if we do the integral from minus a to plus a of f, then that's going to be 0. Okay, for instance, with the second one, if we were to integrate x from minus 1 to 1, you could look at the triangles. You would see there's a triangle below the axis, there's a triangle above the x-axis. The signed areas are going to cancel. You're going to get 0. If you integrate from minus 10 to 10 of x cubed, for instance, you would get 0. If you integrate any odd function around something that's symmetric about the axis, we get an even amount of negative signed area and the same amount of positive signed area. So the signed areas are going to cancel. We get 0. Okay, and how do we prove these? I'm not going to go through the steps, but we would write this integral from minus a to plus a as an integral from minus a to 0 plus an integral from 0 to a. And then on the piece from minus a to 0, we would make a substitution u equals minus x. And then we would see how it plays out. In this case, we would use the thing about f being even, so we can simplify f of minus u to be minus f of u. Sorry, to be equal to f of u. We would get this equation. In this case, f of minus u would be minus f of u. Things will cancel, you would get 0. So all we have to do is split the integral at 0, and then on the negative piece, make a substitution, u equals minus x. Okay, but I won't go through that. Anyway, here's an example of an application of the second one. So we have this horrifically complicated integral, the integral from minus 1 to 1 of sine x over 1 plus x squared plus x to the 100 dx. It will be very, very hard to do this explicitly, probably impossible to do it with FTC2, right? There's just no nice antiderivative. But if we look at our function, we see that it's an odd function, right? If we replace x by minus x, on the top we get sine of minus x, and sine is an odd function, so that's minus sine x. So on the top, we keep the same thing, but we pick up a minus sign. And then on the bottom, when we replace x by minus x, we get 1 plus minus x squared, which is the same as x squared, because the negative will be squared and go to 1. And then we have minus x to the 100, so we get minus 1 to the 100 times x to the 100. Okay, again, we have an even power of a negative number that's going to go to 1. So on the bottom, we still have 1 plus x squared plus x to the 100. So if on this function, we replace x by minus x, we add a negative sign on the top, we don't do anything on the bottom, that means we get an odd function. So here we're integrating an odd function, even though it's rather a complicated one, we have an odd function, and an interval minus 1, 1 that's symmetric about x equals 0. Okay, so according to this rule, we are going to get 0. So if you're ever faced with some kind of crazy complicated integral about something that's symmetric on the axis, it's worth checking just to see if it's odd, because that will give you an easy way to conclude that it's 0. Okay, so in this video, we saw the integration by substitution for definite integrals, and it was just like with indefinite integrals, except when we transform to an integral with respect to u, we should also change the limits. The new limits in terms of u are the values of u at the old limits of x. And then once we transform the limits, we don't need to go back to the original variable, right? So we can find an antiderivative with respect to u, and then plug in the u limits and subtract them to get our answer. Okay, thanks everyone. See you next time.